Welcome back! In the last lesson, we stopped and posed ourselves this question. How exactly does backpropagation work, and how do we actually use it to train our deep neural network? Well, you may recall that I said backpropagation is simply the reverse of feed-forward. With feed-forward, we can predict the outputs for all of our training data. And now, based on the outputs of all of our data points predicted by this model, by comparing the predictions to the actual outputs of our labeled data, the more misclassifications there are, the larger the error, which more specifically is calculated with the cross-entropy formula. The average of the ln of the predictions of the points being in class 1, plus the ln of the probabilities of the points being in class 0, and just like with the single perceptron, we'll apply some form of gradient descent by taking the gradient of our error function. We mentioned that for the single-based perceptron model that the negative of the gradient takes us in the direction that minimizes the error the most. The same concept applies here. The gradient is simply the derivative of the error function with respect to all the weights in our neural network. This might seem complex, but all you need to know for this is that we use the gradient of the total error function and backpropagate it in a reverse feed-forward operation to update the weights. And we do this over and over, iteratively, over some learning rate until the resulting model is one that accurately classifies our data. That is all we're going to cover for deep neural networks. To get a sneak peek of all this, we'll go to playground.tensorflow.org. And this playground allows us to create our own neural network and see how the neural network is trained to fit some data set in real time. As you can see, there's many types of activation functions. We'll mostly make use of the ReLU and sigmoid functions throughout this course. But let's go ahead and ensure all nodes use the sigmoid function since that's the one that we're most familiar with at the moment. And we will have a learning rate of 0.03. That seems pretty reasonable. So we'll leave that. And the problem type we can simply leave as classification, since that's really all we've been dealing with, and we'll choose this circular data set. This works as well. You can go ahead and choose any set of data you want. We're going to stick with this one for now. And now the goal is to define a nonlinear boundary that separates the blue dots from the orange ones. We need a nonlinear model which best classifies this data. And to do this, we're just going to have a single hidden layer. Let's take this one off. This nonlinear model is going to be obtained from the combination of 4 linear models. Before we run this, notice how each one starts with some random model. Now if we run it through backpropagation, it's constantly updating the linear models in our hidden layer, which are then combined to form our non-linear model, which, as you can see, classifies our data pretty well. You just trained a neural network and did it in real time. Now what if instead of 4 models in the hidden layer, I use 3? Let's run this. It's going to eventually train itself to form a triangular-like shape around the inner region. Let's just wait for it a little bit. Actually, I'll just fast forward this video until it does. And there you go, which makes sense because if you really think about it, if you combine these lines right here, it would indeed form a triangular region. What if we use 2 models? In this case, it's just not going to work. You could run this for however long you want. It's not going to separate these 2 regions. You can train the neural network all you want. No matter how many times it backpropagates the errors and updates the weights and biases, if you combine these lines, there is no way they will combine in a way that separates these 2 regions. You need at least 3 models or more. I found 4 to be a better choice to form a more circular decision boundary, since remember 3 was more triangular in shape. Now sometimes our data is so complex that you're going to need a lot more hidden layers with a lot more nodes. Since the more hidden layers you add, the more models you have that can combine to create even more complex nonlinear models, the deeper your neural network gets. And the deeper your neural network, the easier it is to obtain more complex models which classify very complex data sets. Eventually, if we train this neural network, it ends up classifying our data pretty well. In the next video, we'll jump into our code, build and train our own neural network to classify this data. I will see you then.